One of the questions that comes up is what happens if you get the derivative of the derivative? Well, if you have a function, let's say f of x, and you get the derivative of that guy, that's f prime of x. Okay, but actually you can get the derivative of the first derivative, and that would give you the second derivative. And the way you denote it is you say it's f double prime of x, or the second derivative. And if you continue doing this, you can get the third derivative, the fourth derivative, and normally the way you write it is once you get past third or fourth, you start putting little numbers. So if you get the derivative of the second derivative, you get the third derivative, and the fourth, and so on and so forth. So you can do this, you can do this for as long as you want. Now, what does it tell you? Well, remember, let's use a simple situation. Let's say you have the position function. Let's call it s of t. And remember that if you get the derivative of the position, that gives you the velocity. So the rate of change of the position is simply velocity. Okay, but what if you get the derivative of the velocity function? Well, that should give you the rate of change of the velocity. How fast the velocity is changing? Well, what's the word for that? Starts with an A. What is it? What is it? Of course, the acceleration. So the acceleration tells you how fast, not your object, but how fast your velocity is changing. The rate of change of your velocity is the acceleration. And of course this would extend to other situations as well. So let's say, for example, let's say we've got a frog on water, and the motion of this frog on water is described by this function. Now, we want to find these guys, the velocity and the acceleration functions, and then we want to find the acceleration after 3 seconds, and we want to find the acceleration when the velocity is equal to 0. Okay, now let's do part A, and then we'll draw a little picture of this guy, and then we'll talk about all the different little nuances that we're presented with. Okay, so we have the velocity of this guy, which is the derivative. So I'll just use the power rule. So this is 3t squared minus 3. And then the acceleration is the derivative of the velocity, like we said earlier, which is going to be 6t. Okay, so now let's draw a picture of this guy. Now you can draw your picture using your graphing calculator if you want. And so I'm going to graph this guy, and it looks something like, just roughly looks something like that. Okay, now let's just interpret it starting from 0, and let's try to figure this guy out. So first off, the fact when this guy is negative, when the position is negative, all that means is that the frog is going in a backwards direction. So like, for example, the positive y values mean that the frog is going forward, and the negative y values over here just means the frog is going backwards from his starting point. So here, for example, the frog goes backwards, and then at this point on the intercept, he's back in the original position exactly where he started with. And then here he starts going forward. Okay, now, so with that in mind, we'll just keep the picture and we'll answer the questions that were being asked and then try to give some insights as we go along. Okay, so now the acceleration after 3 seconds, and let me just sort of point out, this is 1 is around right here, 2 is over here, and then 3 is somewhere over here. So at 3, you can plug it in to find out, but frog is well on his way. Okay, so now the acceleration after 3 seconds, well, I would plug in 3 into the acceleration function, and I would get 18. Now, before I continue, I didn't quite give any units, so let's say, so t is in seconds, and then s is going to be in, let's say that's in feet. Okay, so if the acceleration is 18, then that would be 18 feet per second squared. So what that means is that the velocity is increasing at a rate of 18 feet per second for every second. So this frog, he's hauling, so what that means is that so the next second, this frog is going 18 feet per second faster than he was a second before that. Craziness frog right there. Crazy frog. Okay. Now, part C says, what's the acceleration when the velocity is 0? Well, before we can do that, we have to find when is the velocity equal to 0. Well, the velocity, which is 3t squared minus 3, equals to 0. That's our question. So if you solve for this guy, bring over the 3 and then get the square root of both sides, you would get t is equal to plus or minus 1. Okay, so we can see that from our picture right here. When t is equal to 1, that's right there. And also -1, but like we said, we're not going to pay attention to this side. So I'm going to simply erase this guy. Now let's talk about this guy, see if that makes sense. Well, if you think about it, it does make sense, because notice that the slope of the tangent line, which is what the first derivative or the velocity is equal to 0. So that makes sense. And so this is the spot where the frog is going 0 feet per second. So notice that here the frog is going backwards. This spot right here, that's a spot where he stops and starts going in the opposite direction to go back to where he originally started. So here he's going backwards, and he starts going back towards the original spot. So he's still, this is where he starts going backwards, so he's still located behind where he started, and but here he's made it back into his original spot. Okay, so the acceleration when the velocity is 0, so we can find that. That was only part of the question. So the acceleration when, since the velocity is equal to 0 at time equals to 1, the acceleration is equal to 6 times 1, or 6 feet per second squared. So what that means is that the velocity at this exact point, even though the velocity is 0, it's increasing at a rate of 6 feet per second for every second. So the next second the frog is going to be going about 6 feet per second. And if you think about it, that makes sense, because take a look. The next second is around 2. So what it's saying is that the slope of this tangent line right here is going to be about 6. Notice also that the acceleration is analogous to the concavity. So here, where it's concave up, that's where the acceleration is going to be positive. Where it's concave down, the acceleration is going to be negative. And you can test that out over here if you would like. So there's a lot to learn about, how to interpret the derivatives. And you, like usual, you learn with practice.